Good morning, everyone. Welcome to Chilling with my Ohmies. My name is Jordan. Thank you for tuning in for this next video. Now, I had shot a longer video here previously, but it was too long and too rambly, so I'm going to make this one a little bit more short and sweet. At the end of this video, we will see a demonstration of my nuclear fusor. So, if you haven't gotten from the title of the video, this is about the Farnsworth-Hirch nuclear fusor. A nuclear reactor you can build yourself if you have the skills, knowledge, money, and most importantly, attention to safety. A very dangerous project. So what is this? This is called the Farnsworth-Hirch nuclear fusor. Now you may be thinking, well, wouldn't this be groundbreaking technology? We hear fusion in the news all the time and yada yada yada. No, it's not. The thing is, fusion you see in the news is usually using something called a tokamak, which is a magnetically constricted stream of nuclear fuel, deuterium or tritium. Deuterium is hydrogen with one proton, one neutron. Tritium is hydrogen with one proton, two neutrons. Tritium is slightly radioactive, and they actually use it in things like gun sights and other things that you want to glow in the dark. But the thing is, tokamaks cost tens of millions of dollars, hundreds of millions of dollars, and they are the size of buildings. And even they have not hit the point of really a return on investment. Yes, there has been some breakthroughs of people, scientists getting more power out than in, but it really is a minuscule amount. But what we'll talk about today is the first nuclear fusor. Is the first nuclear fusion device built after the first atomic weapons were built in the late 1940s, but soon after the fusion was confirmed to be something that can exist and happen. A man named Farnsworth, who also invented the television, the CRT television, Farnsworth. Him and the team, Hirch and the rest of the team developed the Farnsworth-Hirch nuclear fusor. So what is it? It is a high voltage and electrostatic confinement in a vacuum. So instead of using magnetic confinement like you would in a tokamak that the fusion researchers are going for and making progress on, and that I don't understand, this uses electrostatic. So instead of magnetism, we're using electricity. And to be specific, high voltage DC electricity, and I'll get into that in a minute. So you're wondering, okay, how does this device that this random dude built in his basement and other people around the world have built in their basements, how can you make nuclear fusion with such a device? Well, here's how it works. You have a chamber. I like to call it the reaction chamber, but in reality what it is a ultra high vacuum chamber, and we'll get into that in a minute as well. Let me get right out here. So there are two ways to make a Farnsworth-Hirch nuclear fusor. You can have a grounded chamber and one grid, or you could have one high voltage negative grid, or you could have a grounded chamber and two grids like I have. I have an outer grid, which is made of two 2-inch diameter steel rings that have been welded together perpendicularly. And I'll tell you why that design matters in a moment. But here I have my poorly drawn circle, and I charge that to a very, very high voltage positive DC voltage. Okay? And then I have an inner grid, a smaller, which are 2 3/4 inch stainless steel rings perpendicular to each other, welded up by another person on this channel who you'll meet eventually, Dr. Dredman. And that is charged to a high negative voltage. So you have this outer high positive voltage, inner high negative voltage grids. So what's the point of that? The point is particle acceleration. So using some basic science that you learned in middle school or even elementary school, you know that opposite charges attract, like charges repel, positive and negative. Therefore, you have an atom here of deuterium, which is our nuclear fuel. So we have one proton, which is a positive proton, one neutron, no charge, and one electron, negative charged. So you have this atom here. There's the electron orbiting, the neutron, no charge, proton with a positive charge. When it gets close enough to this outer grid, what happens is this outer grid is charged at such a high positive DC voltage, in my case up to 70,000 volts, it rips this electron off of its atom and sucks it into the high voltage, and that ends up flowing out of the chamber into my high voltage power supply. So now you have a proton and a neutron. Well, with no electron to balance the charges out, that's positive charge. So positive charges repel. So not only did this outer grid just steal this atom's electron, and now we have a nucleus in free space, it's also repelling it. And when it repels it, it can either go away and into the chamber wall, into ground. That's no fun, but that happens. Or it can go that way. And if it goes towards the inner grid, what happens? Well, this is a positively charged nuclei. And we also call these ions, because this is no longer an atom. This is just the nucleus. And nuclei are often referred to as positive ions in the electrical world. So the positive outer grid shoots it this way. Well, it gets close to this negative inner grid. Well, guess what? This nucleus is positively charged. This inner grid is negatively charged to a very high voltage. What happens? It gets attracted. So it goes faster and faster and faster into that inner grid. And it goes so fast, we call it going a relativistic speed, because it's going so fast, it's a percentage of the speed of light. There's no other way to describe it. It's going so fast, we count it as a percentage of the fastest thing in the universe, the speed of light. So, if another one of these ions or nuclei or whatever is coming from the other angle, gets accelerated, and they meet in the middle here, well, guess what happens? They're hitting each other at such a high rate of speed, insane rate of speed, that the energy from their collision fuses them from one atom, hydrogen, two hydrogen atoms into one helium atom. Whenever a atom is broken, we call that nuclear fission. Whenever an atom is combined, we call that nuclear fusion. And on that point, don't worry, this is not a fission reactor. Fission reactors are not legal for hobbyists to make for good reason. A fission reactor, such as a uranium reactor, you do something wrong enough and you have Chernobyl on your hands. So fusion reactors are not that way. If something goes wrong, it just breaks and it actually becomes less dangerous because it stops emitting radiation. So when we have these, now we have proton, proton, held together by some gluons, and we have one or two neutrons. Now if you use tritium, which would be one proton, two neutrons, and they collide in the center, they would become helium-4, which is, helium-4 is a stable version of helium. Two protons, one neutron. Two protons, two neutrons. However, I'm using deuterium, so I'm actually creating helium-3, which means, and some helium-4. So the hydrogens, the deuteriums, collide in the center, they fuse, and they create, when they create a nucleus of helium-3, which is two protons, one neutron, what happens to the neutron? Well, the neutron gets expelled. Neutron gets expelled into wherever it's going to go. And neutrons are also known as neutron rays. They are ionizing radiation, and they are the most penetrative ionizing radiation out there. There's very little you can do other than several feet of water or tons of concrete to shield yourself from free neutrons. I do not have that. I do have about 6 inches of water or 8 inches of water between me and my reactor, and that will get a lot of the neutrons, but I will still be getting blasted with neutrons. It's not good, but you can think of radiation, getting radiation into your body, as poison. It's about the dose. If a doctor was to stay in the room and x-ray every patient with x-rays, which are ionizing radiation, and all day, every day, it would be like taking a bartender taking a shot with everybody who is drinking at the bar. The bartender's going to die of alcohol poisoning by the end of the night. Same thing with a doctor. But if you're only there for 1 or 2 shots, you're really not going to die or get hurt in any way, hopefully, unless you're an alcoholic and you keep taking more. But it's the same thing. So if I'm down here every night running this thing, that's a problem. If I only run it once in a blue moon, I should be okay. But there is that danger there with the neutron rays. But that's not the only radiation coming off of this thing. There's also something called Bremsstrahlung radiation. I hope I'm pronouncing that right. Bremsstrahlung. Because remember this little guy, this electron here? He's free too now. So what happens with him? Well, free electrons, if they're traveling fast enough, and in this case they are, that's called beta radiation, or electron rays. Those you don't really have to worry about too much. They have very low penetrating power. Usually just a little bit of lead, or even your clothes can stop them most of the time. So they're not that big of a deal, but once this electron that just got jettisoned from its parent atom smacks into the side of this chamber, what happens is that electron smacking into a nucleus of another atom releases energy in the way of a photon. And a photon is a massless particle of light. Photons, there's a whole electromagnetic radiation spectrum. Most photons are fine. People keep talking about 5G and all these, and your phone giving off deadly radiation. That's not true. It's all about the energy that the photon has. We measure particle energy, including photons. Let's find a spot to write this in. All right, let's do it. Electron volts. And electron volts, is the amount of energy it takes 1 volt of electricity to move 1 electron. So it's a very small amount. So we often see it as kilo electron volts. And if you're really unlucky, you'll see it as mega electron volts. And why I say that is that's because when you're in this mega electron volt range with a particle, you're into gamma radiation and you're in big trouble. But in this case, we're dealing with kilo electron volts, which, consult the chart, are, if they're high enough, are X-rays. X-rays, of course, ionizing radiation, not good for you. You can have a little bit here and there like you do at a hospital, but too much exposure to X-rays or too many X-rays, and you have cancer risk. And in the worst case scenario, you get one of the worst ways to die, which is the worst way to die, radiation poisoning. But in this case, I'm measuring in kilo electron volts, and each time I run my nuclear fusor, according to my measurements, I'm getting about 4 chest X-rays at once. Not terribly bad, but if I do it too often, then I'm going to have a problem. So now the next part that we need to get into is the acceleration of these particles in order to collide and fuse means they can't have roadblocks. So if I have a reaction chamber and there's just these atoms, nuclei, whatever, all over the place, this guy's going to bounce over here, over here, over here, over here, here. And every time he bounces, he's losing energy, he's losing speed, and he's not going to fuse with the other atom, the other nuclei in the center of the center grid. So what do? We simply get rid of over 99.99% of the particles in the reaction chamber. So how do we do that? We do that with vacuum pumps. We have to have a vacuum chamber. It has to be in a vacuum. And you have to get a balancing act right. You have to have enough particles in there of deuterium to create nuclear reactions. But you also have to have not too many as to create pinball action between them. We need to have them to have the straight path towards the inner grid. So we need to pump the atmosphere down to about 1 millitorr or less. And by the way, millitorr is almost nothing as far as atmospheric pressure. Millitorr is used to measure incredibly low pressures, or also known as ultra high vacuum. So millitorr, 1 millitorr is almost nothing. If I'm not, don't quote me on this, but if I'm remembering right, our normal atmosphere that we're in right now is between 700 and 800,000 millitorr. And we want to get less than 1. That is an extremely hard thing to do, and it's extremely low pressure. So how do we do that? We need to attach our chamber to a vacuum pump, but what kind of vacuum pump do you use? Oh, just a piston pump from your from Walmart or Amazon? No. Or what about a more expensive rotary vane pump from Amazon? No. They're not going to get you low enough. They just can't get you at that low of a pressure. So what you need is either a diffusion pump, which I don't have, or what I do have attached to my chamber is a turbomolecular pump. Basically, it's a jet engine. It's got tons and tons of blades down it, and what it does is it doesn't suck. It doesn't have a suction. It's simply any molecule that gets near it, it just smacks it down the line. It spins at 75,000 RPM, 75,000 rotations a minute. That's insane. So insane, in fact, that if you run one at room temperature, it will destroy itself when you're out hundreds or thousands of dollars. It will tear itself apart. So what you need to do is first lower the pressure. We'll put these little fan blades in here, like a jet engine. You got to lower the pressure with what is called a roughing pump, which I just use hopefully you can see this, a rotary vane pump. I got one off Amazon for about 200 bucks. Rotary vane pumps are really good pumps for getting low pressure, but they're not going to get to that 1 millitorr. You can get some really nice and fancy ones that can get down to, say, 30, 15, even like 10 millitorr you can get them down to. But that's not enough, that's not low enough for fusion. So, you hook these together. You turn your rotary vane pump on, and it pumps out air from the chamber, just expels it into the room. And you let that get low enough, and the rating on my turbomolecular pump says it wants it below 700, so it wants it lower than 750 millitorr before you turn it on. Because if you turn it on higher than that, you're going to put pressure on the vanes, the blades, they're going to rip themselves apart, and you have several $100 or even $1,000 worth of a broken pump. So how do I do that? First, I go over here, and I have a vacuum meter. This is a professional vacuum meter, mainly for HVAC, not your average inches of mercury, because we're going way below what an inches of mercury can see. We're going down to this 1 millitorr and below. So I get the vacuum pump. So in order to start this, first thing I do is turn on my rotary vane pump. That expels the air out of the chamber through the turbomolecular pump, which is off, into the room. Once my meter on the chamber is reading less than, for safety reasons, or not to push this guy to its limits, 500 millitorr, then I turn on my turbomolecular pump and it takes me the rest of the way down. So, but it takes me down a bit too far sometimes. Too far so there's not enough particles in here for it to fuse. So I need to bring it up to back to around millitorr again. So what I do is I have what's called a micro needle valve here. And it's a very special type of valve. It's an incredibly low flow air valve. And it's so incredibly low that it's able to take less than a millitorr and raise it up by fractions of a millitorr by turning the valve. Very, very low flow valve. And I have that, the other end of that, attached to a deuterium tank. And now deuterium, the nuclear fuel, you think, oh, that's hard to get. Not really. They use it for many commercial applications, and most gas supply depots and stores carry it, and you can order it. It's not cheap. It's running you usually up to and a little over $1,000 for a canister, but you don't need much, so I just got the smallest one I could. So, the rotary vane pump takes the chamber down to 500 millitorr. The turbomolecular pump takes it down to less than a millitorr. Then I backfeed with a micro needle valve with deuterium into the chamber, which then brings me to about a millitorr, and I can regulate the pressure here to get the equilibrium, because we don't want so many particles, so many of these particles in here that the nuclei are just bouncing like this all the way to the center. Because if they do that, they're losing all their velocity, all their speed to get into the center electrode, center grid, and collide and fuse. They lose too much energy for bouncing around, and guess what? You don't have enough energy, don't have enough speed for nuclear reactions. So, the hardest part of these things is definitely to get low vacuum pressure in your chamber. Ultra high vacuum is incredibly hard to get. The atmosphere hates it. It hates getting to such a low pressure. And 1 millitorr, in atmospheric pressure is, don't quote me on this, between 700 and 800,000 millitorr. So we're going up to almost nothing. And the universe, well, the atmosphere hates this. So what we have to do is stick to all metal. No rubber hoses, no plastic, because rubber, plastic at a molecular level, they're like sponges. They leak out tons of gases. And that's called off-gassing, and it'll stop you from being able to get to 1 millitorr. Yes, this guy can bring you down below that, but only if your system is 100% perfectly sealed. The only plastic or rubber you would ever use in the system, which I use for seals, is Vitron. It's very expensive, but you use it for seals. And it has almost no off-gassing to it. Definitely the hardest part of this entire project. Spent over 2 years on this problem. I tried cookie jar to make fusion. I tried a clear glass tube, and I kept using rubber seals, or I kept using RTV or whatnot. It's not enough. You need steel, you need copper, you need aluminum, you need a minimum amount of Vitron to get a good vacuum seal. It's very hard. And another thing, a big blessing with this, is coating all of my fittings with something called vacuum grease. It's Dow Coring vacuum grease. It's like Vaseline type stuff. It doesn't harden. And that is a great chemical for sealing incredibly hard to seal joints, like we see in like we see in all my connections for my bleed valve, all my connections for my meter. It is a lifesaver when getting a vacuum. Now for the other parts to get are the voltage power supplies. This positive outer ring I have, that is 0 to 70,000 volts DC at 5,000 watts. I ended up getting that power supply. It's an X-ray generator power supply from Chris Bowden for a very, very good price when the Geek Group went under. And here on the outer ring, the inner grid, I have a high negative voltage, and I used a neon sign transformer, one leg of it, so 7.5 thousand volts, 7,500 volts. Then I rectified it with a half-bridge rectifier using 4 high voltage diodes in reverse bias to make a negative. And you take, when you rectify AC into DC, you multiply it by the square root of 2, 7.5K times the square root of 2 is a little over 10K volts. So the voltage, you need about 20,000 or even over 20,000 volts DC in order for this to work. And technically the 70,000 positive, the 10,000 negative makes this a little over 80,000 DC. But in order for an actual nuclear reaction to happen, actual fusor to work, you need that at least 20, preferably at least 30,000 volt DC difference in order to get the acceleration needed to create fusion. So, with all that said, and I hope I covered everything, I'm going to go ahead and get some video of my setup, walk you around Hubert, the nuclear fusor, and I'm going to go ahead and show you him running and the radiation coming off him while he's running. So, stay tuned for that. I'll be right back. Alright guys, here we got the control panel I built, censor that somehow, for Hubert here, the nuclear fusor. I have my vacuum meter here. It is a cheapo, but it will measure down to less than a micron. I have my rotary vane pump power switch, my turbomolecular pump power switch. This says MOT, but it's actually for the NST, for the negative voltage on the inner grid. Then I have phase A and phase B. They're not really phases, they're different legs of 240. And each leg of 240 gets a variac. These are 20 amp variacs, where I can vary the voltage on each one between 0 and 130 volts. At 120 volts, both of them full clockwise, will give me 70,000 volts out the business end of the X-ray generator. And then I have here, this is the volts times 1,000 meters, so I can monitor my voltage output as I run. And this here is my micro needle valve handle here, where I'm able to backfill the chamber with deuterium and control the pressure in the chamber just by turning this guy here. So, under here, we have some business end, a lot of wiring, a lot of switches. We have 2 spools of wire and 2 microwave oven transformers. Though the microwave oven transformers and the spools of wire are actually being used as ballasts, because even with the ballasting, the inductive ballasting, which is pretty significant going to Hubert, at full power I'm drawing 20 amps a leg, meaning I'm drawing 40 amps total even with ballasting of the microwave oven transformers. I made them into a ballast by grounding shorting the output to ground of the case, and then I have one end of power coming from the variac, the other end of the primary going out to the X-ray generator, which gives me some good ballasting. And remember, ballasting, inductive ballasting in AC, is a way to limit current without limiting voltage. So that is my control panel. I gotta stick the valve through here. Don't have the best system for that yet, but hey, it works. And now I'll go ahead and show you my view of Hubert, the reactor, while I'm running. So you can see right here, I need to fill it further up, a fish tank in front of it in order to catch the radiation, the X-rays, and the neutron rays. On the left there, you see the turbomolecular pumps strapped right to the chamber. On the right and on the top are my high voltage grid feed-throughs for the high voltage power I'm giving them. And now, I'm going to cut and we're going to get a video of the back. Alright, now we're back here. Don't kill me about the cable management. Now that it's working, I got to make it pretty. I understand that. But you can see there that orange thing. That is a rotary vane pump I got off Amazon. That's the roughing pump. He does the work of bringing it down to 500 millitorr. And then the turbomolecular takes over from there. This guy here is the turbomolecular pump controller. It takes the 120 AC, turns it to 3-phase AC, and then controls the speed of the turbomolecular pump as it ramps up and ramps down during operation. Here is an old 15 kilovolt neon sign transformer. I have right here a bunch of diodes in reverse bias in order to give it negative DC voltage output and a half bridge rectified. So that's 7,500 AC turns into over 10,000 DC after rectification. That gets powered as well. And down here we have the beast. This is the X-ray generator or transformer. This guy is what it provides with 240 volts at 40 amps in, 70,000 volts at quite a lot of current out. This guy is a beast. He's very lethal. He's actually an older one from 1973. He's done a great job. Great power supply. If you can get something like this for a Farnsworth fusor, I definitely recommend it. And then we have all the power cables hanging here for all the different instruments and equipment. And then this here is some quarter-inch copper line that runs back to the control stand, which allows me to backfill the chamber with deuterium. So, sorry. So that allows me to backfill all the way up to the chamber there. And you can see there that corrugated pipe. That's a stainless steel bellow. That is used instead of any rubber hose because, again, of the off-gassing I've mentioned earlier. So with that, let's get a video of her running. Here we go.